Towards the end of the 18th century, the whole of Europe was astonished by a new and strange device which had been invented in England, the steam engine. It transformed simple workshops into industrial-scale factories. While practical men built engines that were growing more powerful all the time, theoretical scientists had a problem. They couldn't explain exactly how the steam engine worked, nor could they really say what heat actually was. It was not until the middle of the 19th century that answers to these questions began to appear. They were answers which we still accept today. Among the scientists who helped formulate them, a major role was played by James Prescott Joule and William Thomson. Scientists had long debated what heat actually was. Heat-related phenomena were observed and generalized theories were drawn up to explain them. Those who believed that matter consisted of tiny particles thought that heat has something to do with the movement of these particles. Those who looked at 18th century theories of electricity for an explanation preferred the notion of heat as an imponderable fluid, by analogy with contemporary ideas of electric current. It was only when new instruments came along that researchers were able to come up with quantitative measurements, the precondition for adequate explanations. Thus, the Scottish scientist Joseph Black, using the newly invented thermometer, realized that while the temperature of a body could be measured, this was not the same as the heat which it absorbed. When ice melts, some of the heat it absorbs remains hidden. If heat is applied, the ice certainly melts, but the thermometer still reads 0 degrees. In 1780, the French scientists Antoine Lavoisier and Pierre-Simon Laplace developed their ice colorimeter. This measured the heat given off by a body. They noticed that the same mass of copper or wood at the same temperature melted different quantities of ice. At this time, an American-born British scientist in the service of the King of Bavaria, Sir Benjamin Thompson, also known as Count Rumford, already claimed to know what heat was, namely the result of the movement of tiny particles. He set up an unusual experiment to prove his theory. He rotated blunt drill bits inside cannon barrels. The barrels heated up. The Count then measured the degree of heating indirectly by seeing how much water was needed to cool the barrels down. The experiments were impressive, but the Count failed to convince his contemporaries. Few were prepared to support his theory of heat. On Christmas Eve 1818, James Prescott Joule was born in Salford near Manchester in the north of England. His father was a wealthy brewer. Joule received a first-class private education. His tutor in arithmetic, geometry and chemistry was John Dalton, probably Manchester's most famous scientist. He also encouraged the boy's inquiring mind. Joule's father set up a laboratory of his very own for him. Manchester was a rapidly industrializing city and full of the latest technology. Young James was fascinated. He watched the first steam locomotives and was able to study a steam engine in the family brewery. To start with, though, he was captivated by something else, very fashionable at the time, namely the use of magnetism and electricity to carry out mechanical work. The famous English scientist Michael Faraday had shown the way in 1821 with the invention of his first prototype, and since then numerous scientists had tried to develop a practical electric motor. It did not take Joule very long to discover that the battery-driven electric motor was not economically competitive with the steam engine. Its consumption of zinc and acid was too high. But he was fascinated by one observation. He noticed how, when the motor was running, the battery and the cables warmed up. Could that be the reason for the inefficiency of his electric motor? For months on end, Joule carried out a meticulous series of experiments passing current through metal wires of various materials, length and thickness. Each time he measured the resulting heat. His investigations led in 1841 to the law named after him. The rate of heat produced in an electrical circuit rises proportionally to the resistance, the square of the current, and the duration of the current. Having formulated his law, Joule continued measuring heat production during various processes. For example, when a turbine was turned by water. In this experiment, the work done can be measured very easily. The drive is provided by two lead weights hanging on reels of string. Joule could calculate the mechanical work from their weight and the measured drop. The falling weights set the turbine moving. Joule now compared the resulting heat with the mechanical work needed to drive the turbine. In practice, it was not so easy as all that. The temperature rise is extremely small. Joule needed very accurate thermometers, which he had specially made. Finally, he succeeded in establishing an unambiguous relationship between work expended and rise in temperature. He had discovered what is known as the mechanical equivalent of heat. A particular amount of mechanical work generates a particular amount of heat. It was a significant discovery, and in 1978 the International Unit of Energy was renamed the joule in his honor. Joule wanted to make his findings known to other scientists, but as an unknown researcher without a college degree, he was largely ignored, particularly since his theory of the generation of heat contradicted what was then the conventional wisdom. But one young up-and-coming scientist did take notice of Joule's experiments. His name was William Thomson. Born in Ireland, William Thomson began his studies at Glasgow University in Scotland before moving to Cambridge. After spending a while in Paris to learn experimental techniques, Thomson was made Professor of Physics in the University of Glasgow at the age of just 22. Already as a student, he had devoted himself with great energy to the investigation of heat. In Paris, he had tried to discover the manuscripts of an almost forgotten French scientist, Sadi Carnot. In 1822, Carnot had published his theory of the steam engine, comparing it with water power. Just as water streamed down from a certain height and thereby turned a water wheel, he said, in a steam engine, the heat streamed down from a high temperature to a lower one. And just as no water was lost in a water wheel, no heat was lost in a steam engine. Carnot pointed out that any heat that was absorbed during the mechanical work process always had to be liberated again. In other words, Carnot's theory assumed a closed cycle. The heat was present from the beginning and did not have to be generated. Thomson thought this contradicted Joule's idea because Joule had shown that when mechanical work is done, heat is produced. It took Thomson 4 years to arrive at the solution. Both Joule and Carnot were right. It was merely a question of properly combining their approaches. So Thomson developed his thermodynamic theory of heat from two basic principles. The first summarizes Joule's results. Heat is just one form of energy, one which is produced when mechanical work is done, for example. If we look at a closed insulated system, the energy within it can be changed from one form to another, but the total amount must remain constant. The first law of thermodynamics is therefore called the law of conservation of energy. The second law, as formulated by Thomson, brought together Carnot's observations. Heat, he said, could never be totally transformed into mechanical work. Some always remained unused. Every heat engine lost some of the heat applied to it in the form of radiant heat. Energy transformation was therefore not a reversible two-way process. Other scientists were coming to similar conclusions. The German physicist Rudolf Clausius actually anticipated Thomson by a year with his own publication. The first law of thermodynamics in particular has many fathers. For example, the German doctor Julius Robert Mayer. But it is indisputable that James Prescott Joule performed the most careful experiments on which to base his opinion. However, thermodynamics doesn't say anything about the nature of heat, but concerns itself only with measurable quantities and the relations between them. Joule himself went a step further, though. He took up Count Romford's notion that heat was the result of the movement of tiny particles. Joule's first approaches were still very vague, but once the laws of thermodynamics were established, developments were rapid. However, it was to take years before scientists could adequately formulate and prove the theory that heat consisted in the movement of atoms and molecules. Joule and Thomson, by now close friends, devoted themselves in the years to come to other experiments on thermodynamics. These followed on from early experiments that Joule had conducted, and were designed to investigate how changes in the pressure of a gas led to a change in temperature. They allowed air to stream into a tube. The air passed through a narrow opening into a glass retort. The pressure in the tube was higher in front of this narrow opening than behind it. The sudden loss of pressure as the air passed through led to a change of temperature. In the case of air, to a reduction. The air was cooler. Their research project lasted 10 years. They even managed to secure state funding. This allowed them to buy steam-powered pumps. Previously, they had had to pump all their gases by hand. Even though the cooling effect discovered by Joule and Thomson, and named after them, is extremely small, it turned out 40 years later to be of enormous importance. In 1895, the German engineer Carl von Linde applied the Joule-Thomson effect a large number of times in succession, with the result that he succeeded in cooling the air to the point where it liquefied. Even today, gases are still liquefied by this process before being stored in tanks or canisters. With their lengthy investigations, the two friends, James Prescott Joule and William Thomson, succeeded in making a decisive contribution to the development of thermodynamics. The two laws, especially that of conservation of energy, became the foundations of modern physics. Joule spent his final years in modest circumstances. He lived off a small pension granted by Queen Victoria and died in Sale near Manchester in 1889. His friend William Thomson survived him by many years. He was knighted, becoming Sir William in 1866. Then in 1892 he was ennobled, acquiring the title by which he is known to the world today, Lord Kelvin. He died in 1907 and was buried in Westminster Abbey, right next to his great predecessor, Sir Isaac Newton.